Where we finished off at the end of last class was we had analyzed this NPN BJT current mirror and found that with beta equal to 100 for all of our transistors, we saw an error of 4.762%. So that our copy current I1 and I2 were ballpark 5% lower than we expected them to be. So what we're going to kick things off with today is talking about how to mitigate that error. And the short answer is what we are going to do is we are going to include what we're going to call an emitter follower transistor. All that really means is that we are going to insert another transistor into this feedback loop, which is going to help supply some of that base current, okay? So what that's going to look like, not going to be a jerk and just copy this because you guys get mad at me, is something like this. So we have our reference current. Here is QREF. And then what we're going to have is a transistor right here. It's also going to be an NPN. So this whole thing up top is now VCC. I'm going to call this guy QF for follower. And then the rest of the circuit is literally going to be exactly the same as what we had. Here's I1. This transistor had an area of twice AE. This one had an area of 3 AE, where this guy was Q1. This guy had an area of 5 AE, carrying a current of I2, which makes this Q2. And our base needs to be connected together. So this is still going to be node X, but now I'm going to call this node over here on the left node Y. So in our previous configuration, effectively node X and node Y were at the same potential. Now the voltage at node Y is driving our transistor QF, which is responsible for supplying the majority of our base currents, okay? All right, so what we're going to do now is we're going to analyze this circuit to determine the error. But before we do that, I want to label a couple of things here, all right? So this current here is still IC ref. Now we have a current ICF, a current IEF, and a current IBF we need to concern ourselves with. And then leaving node X, we are going to have a current of IB ref, a current of IB1, and flowing down and around a current of IB2. All right, so we are going to still work this problem where all of the betas are the same for your homework. I'm probably not going to be so generous and just make the betas for some things different, but the methodology is still going to be valid. And speaking of homework, expect to see one up sometime this weekend that'll be due next Friday. All right, so the first thing that we need to observe is that the base emitter voltage for our reference transistor QRef, our transistor Q1 and our transistor Q2 are all the same. And so what that tells us is that I1 should still be equal to 3/2 IC ref, and I2 should still be equal to 5/2 times IC ref, right? So if we apply Kirchhoff's current law at node X, what we see is that our current IEF is equal to IB ref plus IB1 plus IB2. We all okay with this? All right, so my goal now is to make some minor relationship changes here, okay? I'm going to express the quantity IEF in terms of, so the emitter current in terms of the collector current, because that's kind of our standard operating procedure, right? So how do I express my emitter current in terms of my collector current? What do I need to multiply by a factor of? Beta plus 1 over beta, or 1 plus 1 over beta, which are the exact same thing, right? Because the base current is 1 over beta times the collector current, and the emitter current is the collector current and the base current added together. So 1 plus 1 over beta, which is the same thing as beta plus 1 over beta. So on the left-hand side, we'll have beta plus 1 over beta multiplied by ICF. On the right-hand side, we want to express everything in terms of our current IC ref. So IB ref is simply IC ref over beta. IB1, since the collector current flowing through Q1 is 3/2 IC ref, then IB1 should just be 3 IC ref over twice beta. And similarly, our base current for Q2 should be expressed as 5 IC ref over twice beta. And so just doing a little bit of algebra here, I'm still going to have beta plus 1 over beta times ICF on the left-hand side. And I'm going to have IC ref times 2 over 2 beta plus 3 over 2 beta plus 5 over 2 beta, which means beta plus 1 over beta times ICF is equal to IC ref times 2 plus 3 plus 5 looks like 10 over 2 beta. And I'm just going to leave that like that for now, although obviously we could simplify it to just be 5 over beta. All right, so what I'm going to do now is just going to save myself a little bit of trouble in a moment. From here, we could say that ICF is IC ref times 10 over 2 beta multiplied by beta over beta plus 1, right? So when I divide both sides, when I divide the left-hand side by this fraction, it's like multiplying the right-hand side by the reciprocal. And so this is going to become IC ref times 5 over beta plus 1. We good? Anybody see any mistakes in my algebra or anything like that? All right. So that's what KCL at node X gives us. If we apply KCL at node Y, running out of room here. Let's look at what's going on. This equation is going to be a little bit more brief, right? So we have a current of I ref flowing in, and then we have IC ref flowing out and IBF flowing out, which we can obviously now relate to the quantity ICF. So this is going to be I ref is equal to IC ref plus ICF over beta. Because I'm running out of room on this page, I'm going to go ahead and make a substitution into here. So I can substitute this expression for ICF into here, and I have now everything in terms of IC ref. So that's going to give me IC ref times 1. Actually, let's do it a different way. IC ref plus IC ref over beta times beta plus 1. Lights up my algebra. Good here, Jordan. All I've done is simply substituted it in this guy for ICF and then divided by a factor of beta. So I have 5, this divided by beta plus 1, and then the 1 over beta comes from this guy here. So I don't think I screwed that up. All right. Now we'll factor things out and all that kind of stuff. I'm going to use that beta times beta plus 1 to get me a common factor in my denominator, which I'm going to need to do on the next page. So to recap, we're going to have I ref is equal to IC ref times beta times beta plus 1 plus 5 over beta times beta plus 1. And now we're at a place where we can get our error current, remembering that I1 is 3/2 IC ref, or I2 is equal to 5/2 IC ref. What we can say here is that I ref is equal to 2/3 I1 times beta plus 1 plus 5 over beta times beta plus 1. And from this, I1 is equal to 3/2 I ref multiplied by beta times beta plus 1 over beta times beta plus 1 plus 5. And our error then comes out to be 1 minus beta times beta plus 1 over beta times beta plus 1 plus 5, which in this case is 0.0495%. So that emitter follower transistor does a lot of heavy lifting here to provide all those base currents and minimize that error. Okay, so just one additional transistor really minimizes the amount of error that we see in our current mirror scheme. Okay. Any questions about this? Absolutely. Right here. Anything else? You good though? Go back to the so the 3 halves, the expectation here is that I1 is supposed to be 3 halves IREF. This fraction out here to the right represents the change from that ideal case. So that's why it doesn't show up.
The 3 halves is what we expect.
Yes. If this were working where effectively if the base currents were 0, so in the most ideal case, I1 would be exactly equal to 3 halves IREF. Because the base currents are non-zero, and because all of the transistors share the same base emitter voltage, what we actually see is that I1 is 3 halves IC ref, recognizing that some small portion of the reference current is going to branch off to supply those base currents. And then this guy right here represents the error introduced by supplying the base currents. And this one is significantly smaller than what we saw with our last example, because we effectively have a term of beta squared in the denominator instead of just beta by itself. So adding that extra resistor, or excuse me, adding that extra transistor gives us a square of beta instead of just beta, which makes it significantly smaller. For sure, absolutely. We're going to talk about that in just a couple of minutes. But there might be reasons why you wouldn't want to use MOSFETs. Like if you were trying to make a device. So I think we talked about this briefly at the end of 335 as to why you would ever use BJTs when MOSFETs exist. BJTs handle larger amounts of current better, right? MOSFETs are great for like microamps of currents and things like that, but for power amplifiers, BJTs, or heaven forbid, vacuum tubes all the way, if you need it to be real beefy. Vacuum tubes. It's actually why I got into electrical engineering and then found out we learned literally nothing about them because we've all moved on to solid state electronics. I wanted to make guitar amplifiers. Instead, I just make pedals. They're much easier to understand. So, anywho, all right. So our next topic of the day is the PNP BJT current mirror. We're not going to spend a whole heck of a lot of time on this because it's so similar. So if we need to provide a current source load to an NPN amplifier, we have to use a BJT, or excuse me, a PNP BJT current mirror. So effectively, if we want to put the current source above the transistor as opposed to below the transistor, we have to use the opposite style of current mirror. So in short, that's going to look something like this. where this guy here is Qref, this guy is Q1, and this current flowing down like so is I copy, and I forgot to connect my feedback. And then obviously this guy right here is DCC. But in most instances, this reference current IRF here is supplied by an NPN current mirror. So that we wind up having something like this. So this current is the IRF that's being supplied by our band gap reference circuit. I'm going to call this guy QREF1, and this will be Q1. And then up here, I'm going to have my PNP, like so. Where this is going to be QREF2, and this is going to be Q2, and this is going to be I copy, which that doesn't look particularly good. So let me erase that. Copy. And let's call this I copy P. It'll be approximately IREF, depending on how many things we connect. And this current right here, I'm going to call I copy N, will also be approximately IREF, again, depending on how many things are connected. So to summarize this configuration, this current I copy N is effectively serving as the reference current for this PNP current mirror up here in the top right. So as you can surmise, this also leads to error or problems with the error, in as much as we have this guy supplying base currents for QREF1 and Q1, and then this guy is responsible for supplying the base currents for QREF2 and Q2 and any associated transistors as well. Obviously, we can fix things using the emitter follower resistance as before. So as a example of how to analyze this guy, let's work what I believe to be a fairly straightforward example. Then once we wrap this guy up, we'll move along to MOSFETs. So let's keep things easy breezy here and give everything the same area. So this one will have an area of AE. Connection there. These are all tied together. And let's label some transistors. So this is going to be QF1, Q1, QF2, and Q2. We're going to wind up applying KCL at node X here and node Y here. And our goal is to determine the amount of error or copy current at the output of the PNP current mirror as compared to our original reference current divided by our band gap reference circuit. All right, so a couple of things here, just real quick. Since VBE ref 1 is equal to VBE 1, effectively, since node X is a constant value because this is a DC circuit, the collector current for transistor Q ref 1 and the collector current for transistor Q1 have to be the same thing. That means IC ref 1 must be equal to IC1. And similarly, since VBE ref 2 is equal to VBE2, actually, those should read VEBs. Thank you. I just heard, I think, Gregory correcting me. You're 100% right. So effectively, because the potential difference between VCC up here and node Y is the same as experienced by QRF2 and Q2, these guys have to be carrying the exact same amount of collector currents as well. Okay. These are literally the same assumptions that we worked on all the other ones. I just want to be very explicit about this one because it can be a little bit confusing because there's so many damn transistors doing things. So IC1, excuse me, IC ref 2 is equal to IC2. All right. So briefly, what's our expectation here? What's the ideal case? I copy is exactly equal to Irish. You're 100% right, because all the areas work out to where we should be getting damn near the exact same current at the output as we have that's being supplied. So that is absolutely our expectation. All right, so if we apply KCL at node X, what we are going to have is this current, which is IC ref 1 is leaving. This current, which is IB ref 1 is leaving. And this current, which is IB1 is leaving. Are we all okay with that? So we can say that I ref is equal to IC ref 1 plus IB ref 1 plus IB1. Which we can write as IC ref 1 plus IC ref 1 over beta plus IC ref 1 over beta, which is IC ref 1 times a factor of 1 plus 2 over beta, which which is the same as IC ref 1 multiplied by beta plus 2 over beta, and therefore IC ref 1 is I ref multiplied by a factor of beta over beta plus 2. Are we all okay with this? So effectively, we're getting something that seems reasonable. IC ref 1 is slightly smaller than IREF, which makes sense because IREF is having to supply those base pairs. So this seems reasonable to me. All right. Now, since this current, let's do this in blue. So this current IC1 is effectively the reference current for the PNP current mirror up top, right? And we know that that IC1 is exactly equal to IC ref 1 because our base emitter voltages are the same. So we've effectively well established what the bias current is for our PNP portion, and effectively we just do the exact same math. So from that, we should observe that I copy is literally just beta over beta plus 2 times IC ref 1 because it's literally the exact same math multiplied by IC ref 1, which is I ref times beta over beta plus 2, or I ref times a factor of beta over beta plus 2 quantity squared. And from this, our error E is 1 minus beta over beta plus 2 quantity squared, or 3.883%. We can obviously minimize this error by including those emitter follower transistors. I see confusion on your face. Why is there confusion? No. So the reason why I say the error isn't more is because we're only copying it twice, okay? So in the previous example, we had roughly a 5%, or the first example that we worked, we had roughly a 5% error. And the reason for that is because the copies that we were making were made up of multiple transistors, right? But these are just single transistors everywhere. So we're making multiple copies. So the error is, it's not as bad because we're not copying it as many times. Like if I gave you an example to where we saw that, let's say if this had an area of 1 AE, and this had an area of 3, and then this had an area of say 5, and this had an area of 8, we would see that the error would get bigger and bigger and bigger because we're effectively making more copies and splitting it up and redirecting it as base current. We're not supplying a ton of different base currents, so we shouldn't see that the error is particularly huge. Does that make sense? Yeah, because effectively the less we leach off of this IREF, the smaller our error should be. All right. Any questions regarding this? All right. So our last for the day will be MOSFET current mirrors. This is going to go pretty quickly because, as Mr. Boyle pointed out, there is no opportunity to steal current through the gate. Yeah. Oh, no, there's not no error. It's just not error from that. The error comes from channel length modulation. It's not as bad. All right, so NMOS current mirrors. Okay. So basically, it's going to be the exact same circuit, except that we're using MOSFETs. Big surprise there, right? So here's VDD. Here's I copy. Here's IREF. Let's call this MREF and M1. All right, so for formality's sake, let's talk about what's happening here, okay? This current source, IREF, is causing MREF to carry a drain current of exactly IREF, because there is no current that can branch off and flow into the gates of either of these terminals, right? Since transistor MREF is carrying a current of IREF, there must be a voltage VGS across this transistor's terminals, right? That's a fixed value depending on what IREF is. MREF and M1 have the exact same gate source voltage, so ostensibly they should be carrying the exact same amount of drain current, except when channel length modulation is considered, right? The reason why this becomes an issue is because this feedback path right here forces VDS of MREF to be exactly equal to VGS of MREF. But the lack of feedback here allows VDS1 to move. Okay, so we are going to see a little bit of copy error, completely and utterly due to channel length modulation. And we'll address that momentarily. So let's talk about scaling real quick here. When we scaled BJTs, we did so by connecting BJTs together in parallel. We can effectively do the exact same thing with MOSFETs, or if we are dealing with a microelectronic circuit that's integrated, we can do that exact same scaling by just changing the aspect ratios of the transistors, right? So if, for instance, W over L ref has a width of length of 10 by 2. If W over L1 were equal to 10 by 4, that means I1 would be 1/2 IREF. If the aspect ratio is half as large, the current is half as large. Similarly, if W over L1 were 20 by 2, so if the aspect ratio is twice as large, our current should be twice as large. So this scaling is actually extraordinarily easy to carry out when we're designing CMOS integrated circuits, because it's literally, if we want twice as much current, make the transistor twice as big, or twice as wide, I guess would be a better way to put it. because we're scaling the ratio. All right. So playing around with the aspect ratios allows us to get effectively any current from a reference current that we could want, just like we could get any current that we wanted by scaling both the sense mechanism and the sense transistors and copy transistors in our BJT. It's just a little easier, especially when we have control of the size of the transistors. All right, so now let's talk about quantifying that error, okay? So let's say that we have, actually, let's just leave this as it is, okay? Let's say MREF and M1 are identical. There's no T at the end of identical, my apologies, with lambda not equal to 0, meaning there is going to be some channel length modulation effect, okay? The question that we want to answer is, number one, what value must VDS1 have such that I copy is exactly equal to IREF? Honestly, kind of a no-brainer. And then number two, what error occurs in iCopy if M1 is operating at the edge of saturation? All right, so let's look at one. Okay. So IREF is going to be equal to 1/2 UN C ox W over L VGS minus VTH squared times 1 plus lambda VGS, where VGS is the gate source voltage for literally both of our transistors, so I'm not going to bother calling it VGS1 and VGS2. And our channel length modulation coefficient portion here, so this is, since this is for our reference transistor, typically this would be 1 plus lambda VDS, but this feedback makes VDS for the reference transistor exactly equal to VGS, which is why I'm putting VGS there. Is that clear? Okay. For our copy transistor, I copy is 1/2 mu n C ox W over L, that same VGS minus VTH quantity squared, 1 plus lambda VDS1, where this is the voltage VDS1. So again, not a particularly difficult question. What value does VDS1 have to make these currents identical? VGS, right? If it's got a value that isn't that, there's error. All right, question number 2. they have different aspect ratios, then this term is just going to be different for both of them, right? And that term is being multiplied by this whole thing. So honestly, not a whole hell of a lot more difficult. All right, so for problem 2, what error occurs in our copy current if M1 is operating at this edge of saturation? So what does the edge of saturation mean? Who remembers that? So the edge of the edge of saturation means VDS is exactly equal to VGS minus VTH, right? Because that is the transition point from triode region into saturation region. So at the edge of saturation, IREF has the exact same value. It literally can't change. 1/2 mu n Cox W over L VGS minus VTH squared 1 plus lambda VGS. I copy is carrying a current of 1/2 mu n Cox W over L VGS minus VTH squared times 1 plus lambda VGS minus VTH. And so we can say that that'll work actually. I copy over IREF is simply 1 plus lambda VGS minus VTH divided by 1 plus lambda VGS, and therefore I copy is IREF times 1 plus lambda VGS minus VTH divided by 1 plus lambda VGS. So our error is simply 1 minus this term. Our percent error is that. Nothing particularly difficult about it, right? All right. PMOS current mirrors is effectively identical to PNP BJT current mirrors, except we put MOSFETs in. Do we need to go through the motions of drawing that and talking about it? All right, let's do it. Just to say we did it. All right, so for our PMOS current mirrors, that's going to look something like this. Just going to do this real quick like. Sorry, that's not right. There we go. So that's our basic configuration. And again, usually the reference current for our PMOS current mirror is supplied by an NMOS current mirror. So a more practical configuration would look something like this. Again, all of our scaling techniques that we've talked about previously would be applicable here, where we can call this MREF, M1, sorry, MREF1, M1, MREF2, and M2. So again, the only error that we would see would be introduced by channel length modulation issues. All right, so I feel like that's a good stopping point for me today. For Monday's class meeting, originally I had said that we were going to talk about Cascode current sources and Wilson, or excuse me, Cascode current mirrors, Wilson current mirrors, and Widlar current mirrors. I may change that slightly to introduce the concept of Cascode current sources and all that thing beforehand, before we talk about those. So I might change the order of lectures 3, 4, and 5 might get moved around a little bit, but we're going to finish up Cascode things and current mirrors by the end of next week for sure. I'm just going to make sure that everything is structured in a way that makes sense to you guys. All right. So like I said, that's enough out of me. I hope you guys have a great weekend. Expect not an exam, a homework set to be posted. Hopefully by the end of today, but definitely this weekend. That will be due next Friday. It's very likely that I'll go ahead and put your first design project up this weekend as well. And I'm going to make that due sometime around when, like maybe a week after you take exam 1 or something like that, to give you plenty of time to look at it and all that kind of good stuff. All right. Thank you guys.